be providing a brief introduction to power quality, why it is important, why it is something that you should be caring about and you should be taking measures about your power quality issues, and how to measure and diagnose the issues that you may have on your facility related to power quality. Actually introducing our latest release for the power quality analyzers of Fluke product line. So let's go ahead and get started. In a nutshell, let's start with a brief definition of what power quality is. So power quality refers to maintaining the near sinusoidal waveform of the power distribution bus voltages and current at a given magnitude and frequency. So in an easier way to put it, it's basically ensuring that the voltage that is being delivered to the users and that is circulating in the electrical network has the quality that it needs to. It's a sine wave, an almost perfect sine wave, because that's what most equipments are designed to work with a perfect sine wave. So the closer we are to the sine wave, the more reliable and more efficient operation we will have with our equipment. Okay. So this is a kind of a brief definition or a technical definition, but why should we be caring about power quality? Basically, for the proper and efficient functioning of our machines and devices, we need to ensure that the electrical signal meets certain conditions, that it's, as I was saying, the best quality possible. So as the different manufacturers need to meet or design their products to meet certain standards and to meet certain limits, so do the power distribution companies, the power supply companies or utilities that will need to ensure that they are delivering the right power supply to the users that will be actually using that power. So having a close look at what the power distribution system look like, just as a brief introduction for those that are not familiar with that, there are three very distinguishes, three different parts in the system. First one is power generation. In power generation is where we transform fossil energy, nuclear energy, and more renewable energy into electrical energy. Now that electrical energy needs to be transported to the end user from the point it is generated to the actual end user that will be taking that power and using it for other purposes. So in order to do that, utilities, power supply companies, what they do is in order to reduce the distribution costs, the transmission costs, and at the same time reduce energy losses, the first thing they do is increase the voltage of the signal to over 100 kilovolts, high voltage, generally speaking, so that we can transport that energy, minimizing the energy losses and with thinner cables, with minimizing costs as well. So that is transmitted. Using transformers, that voltage is elevated to over 100 kilovolts in general, and that power is transmitted through the electrical lines until we reach an area closer to the end user. Okay, so all that part from generation to the end user is called transmission. Once we are closer to the user, then the opposite conversion takes place. So the high voltage is stepped down, is reduced to low voltage, so that end users can safely use that voltage to convert that electrical energy into other sources, into other kind of energies like mechanical for motors or heating or lighting or whatever the user needs to use that electricity for. So that's kind of the overall high-level view of the distribution system. Now, if we take a look at how it is, how it looks like, we can probably immediately have a first idea on the different approaches that we have. In power regeneration and in transmission, and even in distribution, the focus and the main concern for the utilities is to ensure that they deliver the proper voltage signal to the end user. So a quality voltage signal to the end user. While the end user is the one that will be consuming that energy and will be drawing current from the system. So that voltage level, that's quality of the voltage that needs to be delivered to the end user, needs to be maintained regardless of the current that is being drawn by the end user. And nowadays, with much more complex loads on the end user side, because of the drive to save energy, the drive to use efficient machines and efficient devices, that is becoming more and more complex. So the current that is being drawn may be affecting the voltage that is being delivered. So it is, this balance between voltage generation and current consumption, current demand, that the different players need to work with. And which are the different players? The three main players that take part in ensuring that power quality, our power distribution system has the quality it needs, are, of course, the utility company, the power supply provider, which again, its main focus is on delivering quality voltage signal to the end user. Then we have the manufacturers of the equipment, machines, devices that we actually connect to the network. In that case, that manufacturer needs to comply with given standards to make sure that they don't introduce noise and do not create power quality issues into the network. And then we have the end user, who is also one of the main interest parties in this area, where they are just actually connecting all the equipments to the network, and they are using those equipments for different purposes. As I was saying, for lining, heating, production, if we are talking about a manufacturing facility, and so on. So let's take a look at what role these parties play in the power distribution system, starting with the network operator, okay, the power supply company. Again, the main focus of the utility company is providing a quality voltage signal to the end user, okay? They are focused on the voltage. Now, the other focus is making sure that the network impedance is as low as possible, because that means that it's a safer network, and we will ensure that power quality is much better if we reduce the net impedance of the distribution network. That's the second focus. And of course, they are also responsible for maintaining and having redundancy in the transportation, the transmission and distribution system, to make sure that there is continuity in the service. So those are the main responsibilities of the network operator or utilities. If you want to use a single quote for their concerns, and their main focus is, again, deliver a quality voltage signal to the end user. That's the main focus. Then we have the manufacturer, where there are two main areas they need to ensure. First is make sure that they are not a source of emitted noise, emitted quality issues into the system, that they are not injecting power quality issues into the system. And again, there are different standards they need to comply with, different tests that they need to run with their units, with their equipments that eventually will be plugged into the system, to make sure that that is the case. There is a second implication that they will need to make sure that it is that way, which is basically manufacture devices that are not very sensitive to potential power quality issues in the power supply. So if there is a slight drop in the power, in the voltage signal, the equipment would need to keep working, should not break down or create potentially unsafe situations to the end user. Okay, so there is this need for certain immunity from the equipment as well. And then there is this third party, which is the end user, whether it is domestic user, commercial user, or industrial user. In all those cases, the user is responsible for connecting the loads to the system. So the end user has little influence on the voltage signal, but they do have influence on the current signal. And they certainly have a lot of influence on the current signal. If we look at the Ohm's law depicted here, where the voltage component can be taken as the voltage that is being provided by the utility, and then the resistance is the combined impedance of the network and the end user, then we can see that whether or not that effect that the end user has on the current translates into potential voltage issues depends on the impedance factor. So the higher the impedance, the more likely it is that a current issue generated by the end user, by the current drawn by the end user, potentially creates issues with the voltage signal as well. So end user needs to make sure that their installation system, the electrical installation in their facilities, is high quality, and meaning that the impedance is as low as possible. Okay? And it's not only the amount of current that is being drawn by the end user, but also the number of equipments that are being connected to the system, which play with each other, creating its own kind of subsystem. And that can, interact with the electrical system, the electrical distribution system, creating some issues that may potentially be translated to other users, or even translating to some of the issues that we will be checking right now. Okay. Some of the issues that the end user can see, and pretty much, the end user is the one that is going to be seeing them, but can be caused by the manufacturer of the equipment as well. Okay. Generally speaking, is the end user who creates those issues because of a bad installation and bad practices, or the loads that they are connecting in their system. But it may be coming from any of the three parties that I was mentioning. So the point is that for power quality, we can only see the symptoms. We can only see the manifestations of power quality issues. Some of these are flickering, for instance. Some of us are already familiar with this, of course, with flickering of lights. That is coming from issues with the power supply, with the power quality of our installation. But also, there could be higher vibrations, higher noise emitted by electrical motors, for instance, or increased heat in our conductors, our cables, our transformers, electrical equipment in general, that can be also produced and caused by power quality issues. Not to mention unexpected tripping of our protective units, like RCDs or circuit breakers, that we have always experienced some of this tripping without any particular reason, right? So in many cases, if we are seeing these devices that are tripping really randomly, it is because we may have harmonics, or we have other issues that are causing high currents and therefore these protected devices to trip. In worst case scenario, we can even end up with potentially unsafe situations, fires, and production downtime, quality losses, and so on and so forth. So it is really important to make sure that we keep our quality under control, our power quality under control, by correctly measuring the right signals and knowing where the potential issues may be coming from. Is it that I'm working with a low power factor? Is it that we are having harmonics because I'm using inverters in my system, I'm using variable frequency devices that are creating these harmonics? All those things are concepts that I need to be familiar with, and most importantly, parameters that I need to measure using power quality analysis like this one, like we see here from Fluke, where we can measure all these parameters and know where we could be having issues and where the different issues that I'm seeing are coming from. So, if we keep our power quality in good shape, if we monitor it and ensure that we take measures to ensure good power quality, we just get the opposite. So we get a lot of benefits. We get better safety. We don't compromise the personnel, our facilities, the environment. It's going to be much more safer environment. Of course, we cut on maintenance and energy costs because systems will work in a smoother way, right? So will work in a more efficient and reliable way. We will extend the lifetime of our systems, our assets, our motors, transformers. They will last longer. So we will be spending a lower amount of time maintaining them, and we'll be investing a lower amount of money in replacing them because they will last more. We can avoid direct penalties that we can get by the fact of having a low power factor. If we have a high reactive power in our system, we may have a power factor that is below 0.9 or 0.95, depending on the situation. In those cases, we may have penalties from the power supply company because that's not something that they want. So we need to keep that in mind as well. We can save on those penalties. Apart from the fact that we can better plan for expansions of our facility, we know the limits of our facility, and we maximize availability of our production because we keep our power quality under control, and therefore we don't have unexpected tripping of protection devices. We don't have assets that are failing, transformers, motors, and so on. So this is kind of a brief summary on power quality. Now, what should I measure in order to know and identify the different issues that may be present at my facility, talking about an industrial customer? There are many parameters. Of course, we can and we need to measure voltage, current, frequency, but also unbalance in three-phase systems, harmonics, flickering, one of the issues that we were mentioning. There are many potential issues that should be present that may be present in our installation, and with a complete power quality analyzer, as with Fluke product line, we can measure all of them in a single shot and later analyze them in software and take the appropriate measures based on our diagnosis on that data. The user eventually is typically interested in logging everything. That's something that we typically get from the user is, I don't want to be selecting the parameters I want to log and I want to measure. Just log everything. I will have time later on to focus on the ones that matter most for me, okay? So that's something that we have incorporated in our product lines as well to make it really easy for the end user not to miss any particular parameter among the more than 500 parameters that we can log with the unit. So let's dedicate a few more minutes to something that is quite common in recent years because of the higher frequency devices and non-linear loads being used in our electrical installation systems, which is harmonics. Harmonics are coming from non-linear loads, loads that are using semiconductors. Whatever we have, a rectifier, diode, any semiconductor device that makes me work in DC instead of AC, that is introducing by default harmonics, which are high frequency components in my signal that have bad consequences for our power quality. They are heating up our electrical system, they are creating noise, they are creating vibration. All the issues that we were mentioning in many cases are related to harmonics. So we need to be able to sample really fast our signals, our electrical signal, to be able to diagnose which harmonics are creating the issues that we are seeing and take the appropriate measures. There are three different types of harmonics. We have integral harmonics, which are really relatively common. Then we have interharmonics, and much more common in recent years is supraharmonics. Supraharmonics are harmonics that are beyond 2 kilohertz, beyond the 50th harmonic. That requires really high sample rates from the measurement unit. So we need a really powerful unit to be able to get those high frequency harmonics. These high frequency harmonics are being created more and more by inverters, high frequency inverters, and electrical charging stations that are much more being used in recent years. So it's becoming more and more important to be able to monitor these high frequency harmonics up to 30 kilohertz, for instance, to know and diagnose those kind of issues. So there are different regulations depending on which party. Basically, there are these standards and regulations that we need to stick to, and then the measurement equipment needs to comply with if we want to be sure that if there is a power quality issue coming from the utility, from the power supply, I can go to the power utility and tell them, hey, this is what I measured. You are providing me with an incorrect voltage signal. It's not a sine wave. You are, providing me with lower voltages or harmonics or whatever I can detect. They will be asking me, okay, how did you take those measurements? Did you use this given standard? So we need to comply with those standards to make sure that we compare measures against those standards and make sure that those are valid. Another thing to keep in mind is safety standards. It's really important, safety. You were talking about high voltage signals, and for Fluke, this is always important. So make sure that you are using the right instrument with the proper category standard. Our product line goes up to category 3 and cat 4, 1000 volts. So it's the highest standard for category in terms of protection for the end user. So always make sure that you have this really indicated in your unit, as you can see there. And not only that, but also make sure that there are independent bodies that have certified that the measurement unit that you are using really complies with those standards. Okay, so always check that the instrument comes with these marks from independent laboratories. So we are just coming to an end of the presentation, just to introduce you to the to Fluke's complete portfolio of power analyzers, power quality analyzers. It's the 1700 series. We have different families in those series, and all of them are three-phase systems, Cat 3, Cat 4, up to 1000 volts. They comply to the different standards. In many cases, they are Class A, which is the highest standard if we want to comply with the way we should be taking those measurements, you know, in time intervals and frequency, sample frequencies and so on. Yeah, just a few words about our latest release, which is the 1770 series that you can see here, which is the most powerful power quality analyzers we have so far, capable of getting analyzing harmonics up to 30 kilohertz, sampling signals up to 20 mega samples per second. That's for transients, where we have really fast signal changes. It has plenty of communication interfaces, Wi-Fi, Bluetooth, GPS for transient synchronization, Ethernet, and so on and so forth. And we focused on making it really easy for the end user to just plug it in and start logging by just including features like guided setup, the possibility of automatically checking the connections through these LEDs indications, automatically correcting the connections in case there is a mismatch, logging all the data with no need to select the parameters that you need. All those features are meant to make it really simple for the end user to just plug it in and start logging immediately, so that he does not miss any parameter. And then it's, of course, it's prepared for future developments and future updates and future standards that will be meant to be used in power quality. So that's everything I wanted to share with you today. Just as a wrap-up, suggestion is that you'd better take steps in monitoring your power quality, knowing where the issues may be coming from, and taking measures to correct those issues, because that will be ensure more efficient operation of your production facility. That will ensure that you reduce maintenance costs and expand and maximize the life cycle of your assets. And try, of course, you don't know what issues you have or where they are coming from unless you measure them. So absolutely, you need to include a power quality analyzer in your instrumentation to keep those under control and know what kind of issues you may have. All right, so that was all for today. Thank you for your attention. And yeah, I will be around for a few minutes. If you have any question, just feel free to approach me. Otherwise, you can go to fluke.com/1717 series for more information on our power quality analysis, and more specifically on our new series of power quality analysis. Thank you.